Hello students. So in this lecture I will be talking about IC process, yield. And this IC process yield is basically the efficiency uh, of IC processing. Now we all know that in IC processing we use silicon wafers. Now the processing of these silicon wafers, there are a number of steps. Now say we start with 1000 wafers and these processing are done in batches. So if you start with 1000 wafers, now based upon certain parameters like electrical tests and the number of defects, area, these 1000 wafers are not, all of these 1000 wafers are not used in the final product. So there are some losses. Now these losses are in fact mm, uh, uh, explained by this process yield. The more is the loss, the less is the yield. And our the reason why this yield is important, because this yield actually determines the cost of the final device that forms. So we will be talking about the yields. There are basically three yields in the IC fabrication process. The first one is called a fab yield. It is basically the wafer fabrication yield. And this yield is basically the ratio of number of wafers out divided by the total number of wafers which with the fabrication started, or starting wafers. Number of starting wafers. The second type of yield is called wafer sort yield, or wafer sort yield, and it is the number of good or functioning wafers divided by the total number of wafers. And lastly, we have something called a pack yield, which is the number of wafers which pass the electrical tests, we call it as E-test, divided by the total number of wafers. Okay, so the total yield is actually a product of these three, that is the fab yield into the sort yield into the pack yield. Okay, and as I've already told you, the higher is the yield, the lower will be the cost of the final product. Okay. Now let us take them one by one. We will first start with the fab yield. And now here each step in the acid fabrication process is called a station. So each step is called a station, and each station has got its yield of its own. So corresponding to each station will have a station yield. For example, let's say there are 500 steps or 500 stations. So the total yield will be the product of that 500 station yields. There are now during the fabrication process it undergoes mainly 5 steps. These steps are oxidation, source and drain mask forming, number 3 is source and drain drooping, number 4 is again oxidation, and number 5 is contact hole. So these are the 5 main steps in the fabrication process. Now suppose you start initially with 1000 wafers and the yield due to oxidation is say 99.5%. So ultimately the wafers which gets oxidized will be 995 wafers because the yield is 99.5%. Now these 995 wafers will be again used in the next step. So in the next step, if the yield is say 97%, so ultimately the wafers that come out of this source and drain mask will be 965. So in that way, each and every step has got yield of its own, and the wafers which come out from the previous steps, they are used as the source wafers, and slowly the yield drops down. So for example, in this case, if it is y1, y2, y3, y4 and y5, so the total yield will be y1 into y2 till y5. This is the so increase in the number of steps usually means that the yield, overall yield, will actually reduce. Now what are the factors that will govern this fabrication yield? So there are basically 5 factors. factors for fab yield. These factors are, first of all, is the number of process steps, number of steps which are involved in the fabrication process. As you have already seen, the higher is the number of steps, the lower is the yield. And as the electronic devices are getting advanced day by day, so in an increase in generation, for example, if it goes from fourth generation electronic device to fifth generation electronic device, normally the process step will be much more, so that will affect the fabrication yield of the material. Second is if there is a breakage in the wafer. If it breaks down, and so that is why, and so it may also affect the, it may also reduce the fabrication yield. So all the wafer handling are automated. To reduce this, we have an automated wafer handling process in the fabrication of acid devices. So automated handling. Third is the variation in process. There are basically specification limits for each process. There is an acceptable range. For example, the number of defects, for example, number of area. What we have to take care is these specifications should not be too tight, or also they should not be too loose. Making it too loose will make it vulnerable to different type of process with different type of new impurities or different type of new defects, different type of new parameters to be generated. So we lose the control, and if it is too tight, then the manipulating or the tuning capability of the device we lose. So shouldn't be too tight, but also shouldn't be too loose, these processes. Okay. The fourth one is the process defects, which sets in during the fabrication process. There can be a lot of defects. It can be a contamination, or it can be an acidated defect. So these defects are mainly either due to the process or due to the source, what type of material we are using. The last one is the mask defect. We are using masks for the fabrication, and it is basically related to lithography. For example, if you're using a glass substrate, so it may cause some cracks. Dust is another sort of mask defect. So these should be so a cleaning process, so regular cleaning and inspection should be there to avoid this sort of defect, this sort of parameter which can reduce the fabrication yield. So these 5 processes are the factors which are related to the fabrication yield. Coming to the sort yield, it is basically dependent upon the electrical functionality of the material, and the factors which are governing is the diameter of the wafer, and the size to area ratio. Or the size to area ratio of the wafer. Okay, so usually we have initially when the fabrication process started, we used to have an 1-inch wafer, then it changed to 12-inch wafers. Nowadays we are using an 18-inch wafer. And another again, so this is not 2 infinite, this is the first one. So other parameters which can govern this ordeal are again the number of process steps. Higher the steps, higher will be the yield. There can be circuit density. There can be again defect density. Crystal defects. And lastly, the process time, or the cycle time. Okay, so these 6 parameters are related to the performance or how the sortie will be. And now there are various models, yield models, which relates the process, the defect density, and the chip size. So yield models. So the first yield model is called the Poisson model. And it actually assumes, based on an assumption, that the defects in the wafer are random, which is in fact not the case, but it assumes, and these defects are basically the killer defects, or the defects which are detrimental to the performance. Now, the probability of a chip having defects for a chip having k number of defects is equal to e to the power minus m to the power k divided by k factorial, where m is equal to small n by capital N, where small n is the number of chips and small n is the number of defects. So this is the defect number, and this is the wafer number or chip number. Okay, so this equation tells you that if you would like to have k number of defects, so what is the probability of these defects to be existing in the wafer. Now, using this equation, if we have no defect, if we would like to have no defects, that means when k is equal to 0, so we'll have P0, and using the equation reduces to only p to the power minus m. This is actually the yield, taken as the yield of the material. Another parameter is the chip defect density. is given as d naught, and it is equal to again n small n divided by capital N into capital A, where A is the area of the chip. And so again this P0, according to this equation, it is equal to e to the power minus A into D0. Now based upon these yield models, we have the pack yield, or packaging yield, now in Poisson's model we assume that the defects are random, but in most cases defects are clustered. So we have a clustered defects. And in this case the yield is given as integration 0 to infinity fd e to the power minus ad into dt, where fd is equal to the distribution of defect density. There is another model called Murphy's model, which assumes that there is a triangular distribution of defects. And according to this model, the yield is equal to 1 minus e to the power minus a d0 divided by a d0 whole square. Now there is another model called the exponential yield model, which is based upon the condition that if there is a high defect density occurs in small areas of sample. So a small area means a high defect density, and it's is given as yield is equal to a exponential minus square root of a d0, and it is also called the seeds model. Okay, so we have got three models: the Poisson's model, the Morphy's model, this is number 2, and lastly the seeds model or exponential model. So this is the three models.